Dear participants, dear guests, ladies and gentlemen, 3 years ago we intended to organize the first material science conference at Macedonian Academy of Science and Arts, but due to the COVID pandemic it was postponed for 3 years. So this year we seized the opportunity to get together. Materials are very important in the development of human civilization. Historians have identified civilization by the name of most used materials. Thus we have Stone Age, Bronze Age, Iron Age, Steel Age, Silicon Age, and Space Age. It is evidently that each age is marked by the advent of certain materials. From early human history, people used only natural materials like stone, clay, skin, and wood for different purposes like weapons, instruments, shelters, etc. Thus the sites of deposits for better quality stones became early colonies of human life. It's Stone Age. However, need for better quality tools led to Bronze Age, when people found copper and how to make it harder by alloying. The use of iron, a stronger material that gave advantage in wars, started after the Bronze Age, known as Iron Age. This enabled the railroads and the building of modern infrastructure of the industrial world. The Silicon Age, known also as Digital Age or Information Age, refers to the late 20th and early 21st century due to silicon being the dominant material. In fact, we are presently in so-called Space Age, marked by many technological achievements towards development of materials resulting in stronger and light materials like composites, electronic materials like semiconductors, materials for space voyage like high-temperature ceramics, biomaterials, nanomaterials, smart materials, etc. So in course of time, the understanding of material properties became important. The combination of chemistry and physics and the focus on the relationship between the properties of material and its microstructure became the domain of material science. Important components of the subject material science are structure, properties, processing, and performance. Innovation in engineering often means the clever use of a new material for specific application. Their misuse often causes various engineering disasters and consequently environmental pollution. So it is very important to know how to select materials what best fit the demands of the design, economic and aesthetic demands, as well as demands for strength and durability. Materials can be classified based on many criteria, for example, crystal structure, their properties, their composition, their use, etc. So I'm going to mention only one of them. In general, metals, ceramics, glasses, polymers, composites, and nanomaterials constitute the main classes according to classification by structure. Dear participants, I remember that as an active professor, as I am not anymore, during my courses in the field of solid-state chemistry, I, as all other professors in this subject in the world, taught the students that the arrangement of the structural constituents, it means atoms, ions, and molecules in the crystals, in addition to other symmetry elements, can be explained by their rotation around the two-fold, three-fold, four-fold, and six-fold axis, and that their rotation around the five-fold and some other fold axis is impossible for geometric reasons. Thereby, I always pointed out to the students that if somebody presents the experimental evidence that it is possible, I mean the existence of five-fold axis, he will be awarded the Nobel Prize. I must admit that I didn't believe that it is going to happen. But it did happen. Namely, on the basis of his results published in 1984 and 1995, in 2011 it was announced that Дан Шехтман from Israel has been awarded the Nobel Prize for discovering of quasi-crystals where the five-fold and some other fold axis exist. Since then, in order to include both ordinary periodic crystals and non-periodic quasi-crystals, the International Union of Crystallography has redefined the term crystal to any solid having an essentially discrete diffraction diagram. Consequently, many textbooks, especially in solid-state chemistry and physics, have been changed. It is very interesting that many leading scientists of that period, including the two-time Nobel laureate Linus Pauling for chemistry and for peace, and also the head of Shechtman's research group, thought that Shechtman had simply made a mistake. Therefore, the head of the group told him to go back and read the textbook on X-ray crystallography, and a couple of days later asked him to leave the bringing disgrace on the team. Furthermore, Linus Pauling claimed at one of the science conferences in front of audience of hundreds that Shechtman is talking nonsense. There are not quasi-crystals, just quasi-scientists. Dear participants, in spite of that, the awarding the Nobel Prize clearly confirmed the existence of quasi-crystals and recognized Professor Dan Šehktman as one of the outstanding chemists at the end of the 20th and beginning of the 21st century. We are honored to have the Nobel laureate Dan Šehktman with us today. He is going to present the opening plenary lecture of the conference. It is for the first time case in the about 57 years tradition of Macedonian Academy of Science and Arts. With us today are also 7 distinguished researchers in the subject material science from Czech Republic, Finland, Italy, Ireland, Japan, and United States of America, who are invited to present their plenary lectures in various fields of material study. One never knows, maybe between them are future Nobel laureates. Finally, additional 18 keynote speakers from the Republic of Macedonia are invited to present results of their investigations in various material science branches. Dear lecturers, thank you for accepting the invitation to attend the conference and present your plenary or keynote lectures. I wish you a successful conference and pleasant days during your stay in Skopje and also during the visit of ancient locality Skopje and some other attractions in Macedonia. At the end, I would like to express my warm welcome and appreciation to you all for your attendance. Now, I am inviting the President of the Macedonian Academy of Science and Arts, Academician Ljubčo Kocarev, to address to the audience.
Dear colleagues, professors, researchers, ladies and gentlemen, on behalf of the Macedonian Academy of Sciences and Arts, I would like to express my sincere gratitude and welcome you to the first Mass Material Science Conference. I honorably welcome all our plenary speakers, which are truly international, coming from 7 different countries. It's my great honor to welcome our first plenary speaker, Nobel Prize winner for chemistry in 2011, Israeli chemist and professor Dan Šehktman. Long before European mathematicians proved that there are only 17 mathematically distinct tessellations of the plane, different ways of filling an area with a regular tilling pattern, medieval mosaicists knew about them all. Moreover, medieval Islamic tillers had also discovered a periodic tilling, which is a way of filling a plane where the pattern never repeats. Western mathematicians discovered these tillings only in 1960, again after centuries of theorizing that such patterns were impossible. One of the magical qualities of a periodic tillings is that they look simultaneously random and regular. As a geometric form of chaos, they are rule-based yet inherently unpredictable. At first, when Western mathematicians, Penrose among them, discovered appearing tillings. These formations were thought to be just mathematically quantitatively, objects that could not be present in the physical world. Prejudice was so intense that when the Israeli chemist Dan Shechtman announced in 1982 that he discovered a new type of crystal with an aperiodic structure, many fellow scientists refused to believe him. Shechtman's quasi-crystal have taught about a paradigm shift in crystallography, in part because now we know that crystals can be chaotic, exhibiting order without repetition. It is my hope that the first material science conference will be able to achieve its objective in providing an effective forum for academicians, researchers and practitioners to advancing knowledge, research and technology for humanity. Last but not least, my deepest gratitude goes to the organizing committee, scientific committee, institutions, companies and volunteers who have directly and indirectly supported the success of this conference. The committee has organized a vibrant scientific program and is working hard to present highly respected, internationally notorious speakers to lead it. Although we try our finest to be professional, on behalf of the Academy, please accept our sincere apologies should there be an inconvenience that occur before, during, or after the event. I wish you a very productive conference with exciting and encouraging discussions, exchange of knowledge, so that together we can anticipate a future of groundbreaking knowledge, research and technology in the field of material science. I wish you a successful and enjoyable conference and pleasant stay in Macedonia. Thank you.
Okay, so I guess with that we can move on to the working part of the conference. And we are delighted to have as our first plenary speaker one of the leading researchers in crystallography and material science, Professor Дан Шехтман, as you already heard from the introductions. I would like to give you a very brief introduction about his background. Professor Shechtman earned his Bachelor's of Science, Master's of Science and PhD degrees at the Technion in Israel in materials engineering. He did a postdoctoral work supported by a fellowship from the National Research Council at the Wright-Patterson Air Force Base in USA from 72 to 75. In 1975, he accepted a position as a lecturer at the Technion and rose through the academic ranks to become first a distinguished professor and was later appointed a Philip Tobias Chair. During his years at the Technion, he also held positions as visiting scientist at several US institutions, including the National Institute of Standards and Technology, or NIST. Then studies and training led him to become an excellent metallurgist and a superb electron microscopist. And in April of 1982, he took a few months from his position at Technion to conduct research in the US. Then it was called the National Bureau of Standards, and now it is known as NIST. The goal of the study was to search for new rapidly quenched aluminum-based alloys. By using transmission electron microscopy, or TEM, at one certain composition of aluminum and manganese, aluminum 6 manganese, that I think we can hear more today, on April 8, 1982, Дан found a 10-fold symmetric diffraction pattern. His further experiment revealed 2-fold and 3-fold axes at specific angles relative to the 10-fold, angles that could only be reconciled with icosahedral symmetry. This discovery was truly revolutionary. It ignited a scientific revolution that changed how we understand solid matter. His courage and clarity of vision during that turbulent and very exciting period of his career have continued to inspire many other scientists. Indeed, the quasi-crystals had been implicated before Дан Шехтман's work, but they were not recognized for what they were. They were either labeled as twins or simply as unidentified phases. Being a very gifted electron microscopist, Дан generated a series of dark field images and also performed a convergent beam experiment. And these results showed that the icosahedral symmetry was not due to twinning, but was present on an atomic scale. He just happened to be the right scientist in the right place at the right time. Dan's discovery was published in the journal Physical Review Letters in 1984, and the paper, has to be mentioned here, was co-authored by 3 other scientists who helped construct a plausible model, provided a mathematical underpinning, and co-wrote the article. However, it is very important to stress here that it was Shechtman who withstood the public criticism coming even from scientists of the caliber of Linus Pauling, as we already heard. Indeed, he was the one who had the tenacity to hold his ground. And in 2011, he was awarded the Nobel Prize in Chemistry for discovering the quasicrystals. In addition to the Nobel Prize, I would like to mention here that Dan has won numerous other prizes for his achievements, including the International Award for New Materials of the American Physical Society in 1987, the Wolf Prize in Physics, which is an Israeli equivalent of the Nobel Prize, in 1999, and the European Materials Research Society's Anniversary Award in 2008. And these are just a few of his awards and honors. And with that, I would like to hand it over to you, Dan. Thank you.
Ladies and gentlemen, distinguished scientists, it's a pleasure to be here. That's my first visit to Macedonia. I always wanted to come here. This is one of the few countries that I never visited before. And I found that you have, number one, a wonderful country. You have a most beautiful city. I wrote my family that I think it is the most beautiful city I ever visited. And I visited many, many cities around the world. And you have nice people here. Thank you for the 3 introductions. So now that you hear all the story, I will show you just the pictures, and that will be it. But the most important thing to know about me, besides the 3 introductions, is that I'm a family person. I have 12 grandchildren, 12. I have 4 children and 1 wife. And thank you, and I'm very proud of that. And I can tell you, as people of science and education, that everybody in my family has a standing order from me. I tell the young ones as they are born, and they started to talk, I tell them, you start your education in the kindergarten, and you finish when you finish your PhD. And there's nothing to talk about in between. Start. And my wife, who is a psychologist, claims that I apply too much pressure on them. But the fact is, it may be true, but they comply. So all of them are well educated. Okay. So my talk is about the discovery of quasi-periodic materials, and I will talk a little bit about the role of transmission electron microscopy, because many of you are material scientists, and you know what's going on. And so let us start. In the mid-80s, there were 3 surprising discoveries on the structure of matter and its properties, and they came year after year, and all 3 of them received the Nobel Prize. Thank you, I was looking for that. All 3 of them received the Nobel Prize. And the first one, chronologically, was my discovery of quasi-periodic materials, and the paper was published in 1984. And the names on that are my name, Ian Blech, and Denis Gratias, and John Kahn. I will tell you a little bit about these people, and each one was very important in the contributions. Next came the discovery of fullerenes, 1985. Harry Kroto, wonderful scientist who died a few years ago, amazing person and a good friend. And then came high temperature superconductivity by Alex Muller and George Bednorz. Now, when high temperature superconductivity was discovered, everybody was happy. because now we can use liquid nitrogen instead of liquid helium in order to generate superconductivity, and that is very useful. When fullerenes were discovered, Harry Cotter told me that the model made some resistance, and there were 6 papers published against the model, but they were wrong, and they were recognized as, Harry Cotter and colleagues recognized as discoverer of fullerenes and the model. But when I published the first and second paper with my colleagues, it met a lot of resistance, and that resistance lasted for 10 years. For 10 whole years there were papers against quasi-periodicity in materials, and I'll tell you a little bit about it. Okay, but in order to start, I will just very briefly define what I mean by order, periodicity, and rotational symmetry. Here we have a two-dimensional array, and clearly it is ordered. What does it mean for you that it is ordered? If I ask you to continue it in any direction, you know how to do that. You can continue it. How can you know? How do you know? Because it's ordered. So you understand the order. There is a rule here of order. That's order. Now, this is not only ordered, this structure is also periodic. So if you look at this red line, there is periodicity, equal distance between these circles. And because it's a periodic structure, in any direction that you choose, you will see periodicity. Periodicity in this direction, periodicity in this direction. Any direction that you choose, you find periodicity. So this structure is ordered and periodic. Let's say a few words about rotational symmetry. I can take this same structure with a little handle, red handle at the top, and I can turn it 90 degrees and it looks the same. 180 degrees look the same. 270 look the same. 360 looks the same. And I can do it 4 times. And this is why this structure has a 4-fold rotational symmetry. Okay, these are the terminologies that I will be using. Now let's say a word about crystallography. The science of crystallography started really in 1912 by a seminal contribution by von Laue, a German scientist, who performed the first X-ray diffraction experiment. And he started the field of modern crystallography because now we had a tool to decipher the atomic structure and order of crystals. And this is 1912 was the year in which the science of crystallography started, and very quickly the X-ray diffraction became the favorite tool, in fact the only tool, to analyze structures of crystals. And this is what I just said. And the crystals that von Laue studies were ordered and periodic. In all the hundreds of thousands of crystals studied during the 70 years between 1912 and 1982, the year of my discovery, all these crystals were found to be ordered and periodic. All of them. There was no exception to the rule. They were ordered and periodic. And based on these observations, a paradigm was created that all crystals are periodic, and the following definition of crystals was accepted by the community of crystallographers and by the scientific community in general. The definition was not based on theory. It was just based on endless number of observations that there will be without any exception. So this was the definition. A crystal may be defined as a solid composed of atoms arranged in a pattern periodic in 3 dimensions. Very simple. A crystal is ordered and periodic. This is it. Why? Because all crystals observed were like this. And here is another definition. Exactly the same meaning, but more different words. The first one is in a book by Kality, the second one is a book by Barton and Masalski, and they have modern editions of these books, as you may know. The second definition says atoms in the crystals are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Exactly the same meaning. A crystal is ordered and periodic, and life is simple. And the science of crystallography was thought to be a mature science. A mature science is a science in which we believe we understand everything. There is nothing new that can happen in our science. It's very simple. We understand everything. We have so many observations that we are sure that we understand everything. And we have a powerful tool called X-ray diffraction, and the field was called X-ray crystallography, based on the tool that was the major tool in deciphering structures. Now, crystallography in 1992, here's a page in a book by Charles Kittel. I know you cannot read it, but now maybe you can. And he says the following: we can make a crystal from molecules which individually, each molecule can have 5-fold rotation symmetry, each molecule. But we should not expect the lattice to have 5-fold rotation axis. Why so? Because in periodic crystals, the allowed rotational symmetries are 1, 2, 3, 4, and 6, no 5, and nothing beyond 6. It was true, it is true. It's simple mathematics, and I will not spend time to prove it to you, but if you look at the literature, you find a simple explanation. It will show you why it cannot happen with 5-fold symmetry. Okay. Now let me just show you a picture. These are carbon atoms in diamond. This is a picture I took very many years ago. I studied diamonds at one part of my life. And you can still see that these carbon atoms are ordered, and you can see the periodicity, and you can see it in this direction, and you can see it in this direction, you can see it in this direction. Any direction you choose, there is periodicity. The order of carbon atoms in diamond is periodic. The allowed rotational symmetries are 1, 2, 3, 4, and 6. 5-fold rotational symmetry, as well as any other symmetry beyond 6, is forbidden in periodic structures, and life was simple. Now let's go to the reciprocal space. This is the space in which the diffraction exists. But I will not show you X-ray diffraction. I'll show you electron diffraction taken by a transmission electron microscope. And here is a diffraction pattern from a periodic structure, not quasi-periodic material. And you can clearly see that the real space and the reciprocal space are similar in several ways. Number one, each dot here is not an atom. This is a diffraction spot. The spot in the center is the transmitted beam, and all the rest of the spots are diffracted beam from a crystal which is periodic in the electron microscope. And what you have here is periodicity in this direction, and in this direction, and in this direction, every direction. The real space is similar to the reciprocal space, and both are periodic. Rotation symmetries that are allowed also in the reciprocal space, 1, 2, 3, 4, and 6. No 5-fold rotation symmetry, and nothing beyond 6-fold is allowed in the real space and in the reciprocal space. And then something happened, and the International Union of Crystallographers issued a new definition of a crystal. And this new definition of a crystal is a poem. Now, you have to understand, some of you are members maybe of the International Union of Crystallographers. This is a serious, no-nonsense organization based on very sophisticated mathematicians. They don't waste words, and they came up with a definition of crystal which to me is a poem. A very soft definition. It does not say a crystal is. No. By crystal we mean any solid having an essentially discrete diffraction diagram. And by aperiodic crystal we mean any crystal in which 3-dimensional lattice periodicity can be considered to be absent. Excuse me? This is the definition of a crystal now? Yes. What happened? Why do we need, before we had such a simple definition, suddenly we need this elaborate poem as a definition of a crystal. And what happened was the discovery of quasi-periodic materials, and now let me take you to 1982. This was the 70th birth of crystallography. Remember, 1912, 1982. And this was the year quasi-periodic crystals were discovered. I now take you to the day of the discovery, and I can take you there because I can show you my logbook from that day. And there is a lesson to the young people among you. I don't see very many, but I'm sure I see some, yes, that are young. And my recommendation to everybody, especially young scientists, when you perform an experiment or you make a calculation, if you're a theoretician, write it down in a logbook. You may remember what you did for 2 weeks, but not 20 years later. But if it is in a logbook, number one, you will remember it. Number two, you can show it. Number three, it's a proof that you really did that. And this logbook, this particular logbook, is a US government official laboratory notebook. And it has so many pages per bundle, so you can count them, make sure that no page were taken out, make sure no page were put in, that it's fraud-free logbook. And I use, this is one of 6 logbooks that I have for my electron microscopy over the years, and it contains a lot of information. Now, this was not meant to be seen by anybody but to me, but now it's free for everybody, and it contains a lot of information. At the top you see that I was working on aluminum 25 weight % manganese, and the date is April 8, 1982. Sloppy handwriting. In the darkness of the electron microscope I make my little notes there for myself. The numbers are plate number of the electron microscope. Those days we took the pictures on glass plates. Some of you may remember those days, the glass plates. Then came plastic film, and of course now you see it on a screen of a computer. You don't. And if you want to record the image now, you push a button and it has been recorded. Those days we had to take the picture on the glass plate, take it out to the darkroom, fix it, first of all develop it and fix it and wash it and dry it, and then take the positive of the negative, and it is a whole process that took a whole day to generate a few good pictures. Now it is a matter of seconds, but it was fun anyway. So let's see. On the in the middle there you see those numbers, 1720 plate number, and so on and so forth. And SAD is selected area diffraction. It's a diffraction pattern. And another diffraction pattern, 1722, 28K means it's a picture with magnification 28,000 times. K is 1,000. Then came 17K, and then came the most interesting 2 pictures, 1724, 36K. I look at the picture on the screen and I say, this is interesting. Today, when people discover something, in many cases, they say, what's going on here? This is interesting, something different. I want to tell you something. It came by chance, but I was ready for it. Other people will look at it and will not realize that something is special there, and I will explain to you what is special there. And then they said, okay, let me take a diffraction pattern, not from the whole specimen, from one part of the crystal. I'll show you the picture. I take a selected area diffraction pattern. This is plate number 1725, and I write 10-fold with 3 question marks, because it has a 10-fold rotation symmetry diffraction pattern. And I said, I know what it is. These are twins. Material scientists, some of you know what twins are. These are twins, and in my previous experiment years before, I had this phenomenon of 5 twins joined in a point, and if you take a diffraction pattern, I will show it to you. If you take a diffraction pattern from all 5, you have a diffraction pattern with a 10-fold rotation symmetry, like the one I see here. And I said, okay, these are twins. I will record them and forget it. And I spent the whole day, from that, the whole afternoon, it was, everything happened in the afternoon. I spent the whole day performing micro diffraction and performing dark field images. I will not go into details. Looking for the twins, and I could not find them. From day one, I knew that there were no twins. I did not know what they were. I did not know what the structure was. But twins, it was not. Why is it important? Because years later, wise people like Linus Pauling and many others said, oh, these are twins, it's well known, no problem. No. There were no twins there. I know it from that very afternoon. In fact, I spent the whole afternoon just trying to find a twin. All these experiments from plate number 726 onwards are designed to find a twin. No twins. Okay. And this is the discovery. Now, when Mr. Archimedes discovered his law of Archimedes, story tells us that he jumped out of the bathtub shouting, Eureka! We don't do that anymore. First of all, who has time to take a bath? We take a quick shower and that's that. But more than that, and this is what I told you before. Today, a discovery starts with the word, what's going on here? This is interesting, something different. You see something different. Okay, so this is him. So this is a picture that drew my attention. And this is the picture. Everything I show you now is original from that day. No, nothing that was done later. What you see here are crystals, and from this structure of aluminum 25% manganese. I will explain to you briefly why I did that. And some of these crystals are pitch black. You see, for instance, in the lower left corner, above the half micron sign, you see a crystal which is pitch black. Now, this is a bright field image. If in a bright field image means taking the image with a transmitted beam. If the crystal is pitch black, it means that the transmitted beam has almost no intensity. So where did the electron go? To the diffraction. So this crystal diffracts heavily, so heavily that the crystal is pitch black, and I have never seen such a black crystal before in my life, and I was very experienced electron microscopy. And I say, wow, that's interesting. So I take a diffraction pattern from that black crystal only, and this is what I see. So I look at the diffraction pattern and I say, well, what is the rotational symmetry? And I start counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, no, cannot be. And the other way, 1 to 10-fold, and I write in my logbook 10-fold rotational symmetry. And so this is electron diffraction from the icosahedral phase. I will explain why we called it icosahedral phase later on. And it has 5-fold rotation axis. It's not 10, it's 5-fold. But you could not tell from this very first experiment that it's really 5-fold. And it is not periodic. You see, if you go along this line, you don't see any periodicity. The distances are not periodic. And if you take distances and divide by one another, then you get that the ratio of distances is really the Fibonacci number tau. And this is an irrational number. This is the wrong sentence to say, that if you measure A divided by B, you get an irrational number. It cannot happen. But of course, the measurements is not very precise on electron diffraction. And by theory, this is a number. So Mr. Fibonacci comes into the game, and I will talk about him. And the ratio is the Fibonacci number tau. I will explain what it means, and it's also called the golden mean. And some people that claim that they understand aesthetics better than other people claim that this number has a special aesthetic properties. Don't argue with them. You lose. So, that diffraction pattern was one of many. Of course, in the electron microscope, you can rotate a specimen and you can tilt it, so you can bring it by the goniometer into different positions. And this is a series of diffraction pattern. On the lower right, you see 5-fold rotational symmetry. As you go up, you see 5, 2, 5 again, and down there you see 5, 3, 2, 3. 2 and 3 are allowed, 5-fold is not allowed in periodic structures. This set of diffraction pattern has an icosahedral symmetry, and I will explain what it is. Just if you look at the angles, you see the angles are marked down there. Okay, this is twins. These are twins in diamond, and on the left you see just a model, computer model of the same. You see the sigma notations, forget about the sigma notations, they belong to another chapter. But you can see there are 5 twins here, and the red lines mark the twin boundaries. This is a part of the crystal, and the relationship between 2 adjusting twins is something like that. We call them twin because they look like twins. I have 2 grandchildren that are twins. So you see that there are 5 of them. If you take a diffraction pattern just from 1 twin, then you get a periodic diffraction pattern. If you take from the next one, you get exactly the same thing rotated 72 degrees. And another one, 144 degrees. And altogether you have all of them, 360 divided by 5. But if you take a diffraction from the center, all of them together, then you have 5 superimposed diffraction patterns, and it will have 5-fold rotational symmetry, of course. So this is what I thought it is, but it was not. Okay. We can skip that one. Now I show you, here is a crystal with a pseudo 5-fold symmetry, like the diamond crystal. This is a crystal in the aluminum iron system, and it is very large. It's really, you see it by optical microscope, very large. And again, the same thing. And if you take a diffraction pattern from all 5 of them, diffraction pattern from the center of all 5 of them, then this is what you'll get. But this is a combination of 5, and if you show you 1, this is 1. The one marked in red is 1 diffraction pattern, and it repeats itself 5 times, and this is why you get this pseudo 5-fold symmetry. Enough of that. 1984, I sent for publication the first paper with Professor Ilan Blech. Ilan Blech was a professor at the Technion. He was the first person who was willing to work with me. This is after my sabbatical at the National Bureau of Standards. I came back to the Technion, showed it to Ilan Blech and asked him, what do you think it is? He came up with a model that could explain how this quasi-periodic structure could exist, and his model was based on joining icosahedra in space, simple icosahedra in space. His model is basically right, but the unit cell is not right, and later on the unit cell became more complicated, and the icosahedron is the complicated icosahedron was designed by Alan Mackay. Alan Mackay is an eminent crystallographer living in England in our time. He's an old gentleman, and he's the best crystallographer I ever met, and he came up with a model that is accepted now. So the Ilan Blech model was correct in principle. That summer of 1984, I was again at NBS. I came there every summer, spent the summers there. And from there, I sent the paper to Journal of Applied Physics. Those days, the older generation among you may remember that scientists could not type. We had secretaries that types the papers for us, secretaries in the office. That's what they did. They were typists. Nowadays, it's difficult to imagine, but this is what they did. So I wrote this paper by hand. The secretary typed it. I corrected it. She typed it again. I corrected it again. She typed it again. The whole thing, again and again. They had very quick fingers. And finally, I had the paper ready. I put it in an envelope, wrote nicely the address, Journal of Applied Physics, stamp, goodbye paper. A few weeks later, I received an envelope from Journal of Applied Physics. My paper is in there with a letter that says something like the following. Dear Dr. Shechtman, thank you very much for your contribution to Journal of Applied Physics. We decided not to send it for peer review because we think that it will not be appreciated by the community of physicists. We don't think it will be interesting for the community of physicists. Okay. So I took the paper and sent it to a metallurgical journal called Metallurgical Transactions. They accepted it and published it, but they published it deep into 1985, and I sent it to them in the end of 1984. Meantime, I showed the rejected paper to John Kahn, my host at National Bureau of Standards, and I said, hey John, why do you think, what's wrong with the paper that it was rejected? He looked at it, he read it, he came and argued with me. Then he said, Danny, we have something fantastic. We have something fantastic here. Let's do something completely different. Publish a short paper in PRL, and it will be a quick, fast publication, and it will be only about your finding from the first day, without the Ilan Blech model, just your findings. And we did. For me, it was a great honor to have a paper with John Kahn. We sent it, it was published in a few weeks, and boom. Towards the end of 1984, hell broke loose. In the paper, which is the second paper, not this one, it is this one here, I described how I prepare a specimen, and people could prepare such specimen in a couple of days, have it in the microscope, and come up with exactly my results. And so from all over the world, I started to receive telephone calls, email, Danny, we have it, this is fantastic. To make a long story short, they took my discovery and turned it into a huge, explosive science. And this science was heavily sponsored in many countries, especially in France. France had 26 CNRS laboratories working on quasi-periodic material. 26 laboratories sponsored to work on quasi-periodic materials. So this was a fantastic feeling, and the names on this one are my name and Ilan Blech, but also Denis Gratias and John Kahn. John Kahn, I explained to you. Denis Gratias he was and still is, a mathematical crystallographer from France. John Kahn invited him to confirm that what I wrote in my paper is correct, and his contribution was to add the mathematical language into the second paper, so he was very important. Anyway, so this is the paper that made the boom. The second paper was published half a year before the first paper. Okay. Back to principle, icosahedral symmetry. This is an icosahedron. It's a platonic body. If you put your eye at the top and look down to from the top to the center, you will see that there is a 5-fold rotational symmetry there. And it has 6 axes like this also on the sides. 6 5-fold, 10 3-fold. The way you look at it, you see the 3-fold rotational symmetry, and 15 2-fold axis. Okay, and the main rotational symmetry of the icosahedron is also on the football, and I'm sure that the best team in your country, I don't know what it is, they don't know that they play with icosahedral symmetry, even if they win all the games. So you can see 5-fold, 2-fold, 3-fold, very nice to explain to young people the rotational symmetries of the icosahedron. Okay, now let's say a few words about quasi-periodicity. What is quasi-periodicity? And to do that, we need to look at the wonderful picture. This is a drawing of Leonardo Fibonacci de Pisa. He was the greatest mathematician of his time, 13th century, and probably the best mathematician many hundreds of years later. He was really number one. And this is a statue. You can still see the statue. You know, behind the inclined tower of Pisa, some of you may want to go and see the inclined tower of Pisa, some have seen it. Just behind it is a graveyard under a roof, very small, under a roof, and this statue is there. It's a large statue, maybe more than 2 meters high, erected in his name. So what is his contribution? Well, his contribution is called the Fibonacci rabbits. So what are the Fibonacci rabbits? And it will show you what quasi-periodicity in one dimension is. This Fibonacci rabbit, what is the story? I will make it very simple. There is one female rabbit. Male are not necessary in this theory, although people who are more politically correct give you pairs of rabbits. So this female rabbit gives birth to a little one every month. The little one cannot reproduce immediately. It has to grow for 1 month, and then it can reproduce. So there is order.
you know how to do that. You know how to continue this. In the first month we have one rabbit, in the second month we have big one, small one. In the third month the big one gives birth to a little one, and the little one grows. In the fourth month, the first mother gives birth to a little one. The little one grows, and the one that grew gives birth to a little one. So these are rules. There is order. But if you look at the last line, I stopped here because this was the end of the page. If you look down there, you see that there is no motif of any size that repeats itself. There is order. You can do it, and if everybody will not make mistake and do it, you'll all reach the same result. There is order there, but no periodicity. There is no motif of any size that repeats itself along this line. This is quasi-periodicity in one dimension. And the numbers on the left are called Fibonacci numbers. This is general knowledge, and they work as follows: 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on and so forth. And equation number 1 says exactly this: an equals an minus 1 plus an minus 2. Okay, but also if you go to infinity, then and you divide the last one, number of the last one, by the one previous, you get this irrational number 1 plus 8, 5, root 5 divided by 2, which is the Fibonacci number, 1.618, and endless number of digits beyond it. And this is the famous Fibonacci number. Leonardo Fibonacci de Pisa, he published this in a book called Liber Abaci, the book of Abacus, the book of mathematics. This book is very interesting. It is not designed to show the rabbit's experiment. This is just a small chapter in this book. The book was designed to tell the merchants of Pisa, his town, to do mathematics using the Indo-Arabic numerals and not the Roman numerals. How can you do mathematics with Roman numerals? And this is what they did. He said, don't do that. Use the Indo-Arabic numerals as we use them today. Boom, mathematics flourished thanks to that. And he published it in 1202, beginning of the 13th century. Quasi-periodicity in two dimensions. Roger Penrose, eminent scientist living in our time, received a Nobel a couple of years ago. Really a British eminent scientist, a physicist, theoretician, practitioner, philosopher. I admire him. And this is Penrose's tiles. He discovered two tiles that can tile a floor according to a certain rule, matching rule. And if you do it right, you'll get a tiled floor, no gaps. And this floor, there is an order there because there is a rule how to put it together. No gaps and no motif that repeats itself in any direction. This is quasi-periodicity in two dimensions. What about three dimensions? Aha, glad you asked. Quasi-periodic crystals is quasi-periodicity in three dimensions. Okay, enough of that. And now to the story, and we'll finish by that. I call it the years of rejection. When I just made the discovery in 1982, I started to talk in the corridors with everybody who was listening about five-fold rotation symmetry in crystal, and there are no twins and so on. And the reaction was mixed. John Kahn, as many others, were very supportive. John Kahn said to me, Danny, this material is telling us something, and I challenge you to find out what it is. He didn't find out what it is, but he was very supportive. And there were other people. Some people said, I'll do the X-ray diffraction, I'll do this type of structure, I'll study thermodynamic structure. So people really helped. But on the other hand, there was also rejection. And just to symbolize the rejection, the head of my group, the head of my research group, was really an administrator. I didn't have any science with him, but I had to report to his secretary. He came to my office one day, smiling sheepishly, putting a book on my desk called X-ray Crystallography. He said, Dr. Shechtman, please read this book, and you will understand that what you're talking about cannot be. And I said, you know, doctor, never mind the name, I know this book, I teach at the Technion, I don't have to read it. I'm telling you, my material is not in the book. took the book back, came back a couple days later, and he said, Dr. Shechtman, I cannot have my name associated with your name. Please leave my group. So I left. Sounds terrible. Really not. All I had to do is to find another group leader who would adopt the scientific orphan, me. I did it in half an hour. Somebody adopted me, so instead of reporting to his secretary, I reported to their secretary. It was like little nothing, and I don't think I even told my wife. It was something not important. But nowadays, when you tell, he was thrown away from his research lab. Yeah, but it was really nothing practical. Anyway, but the feeling was mixed during that period of time. And if you want to see how I felt during these 2 years of between the discovery and the first papers, it is something like that. Okay, this was the first 2 years. And then 1994, the publication, until 1975, there were many people working on quasi-periodic materials, but the International Union of Crystallographers said the following: give us X-ray diffraction from a single quasi-periodic crystals. We believe in X-ray diffraction. We do not believe in electron diffraction. We could not do that because our crystals were too small, and those days we did not have X-ray microbeams like we have today. We couldn't do it. And if you take an X-ray from a group of crystals, you get rings, and you don't see the rotational symmetry. But in 1987, two groups in France and in Japan managed to find stable quasi-periodic materials. It means that they melt congruently, you resolidify them, they're resolidified as quasi-periodic material. That means you can grow crystals as large as you want. Voila. And a friend of mine sent, his name is Anpeng Tsai, he rest in peace, he died young. This is from Anpeng Tsai from Tohoku University in Japan. He sent me these 3 diffraction patterns, 5-fold, 3-fold, 2-fold X-ray diffraction pattern. And I took them to the International Union of Crystallographers meeting in Perth, Australia. This is on the west side of Australia, in 1997. And when I showed this picture, everybody said, okay, Danny, now you're talking. Now we agree that we have to do something about it. They formed a committee that accepted quasi-periodicity into quasi-periodic crystal into the realm of crystallography, and that was a very fantastic step ahead. So you will say, okay, now the International Union of Crystallographers accept quasi-periodicity. Who will object? Well, not so fast, because there was Linus Pauling. Now, Linus Pauling was arguably the greatest chemist in the 20th century in the United States. He was the head of the American Chemical Society. He was really admired by many. And when he started to write papers against quasi-periodicity, the attack was directly on me first, but then on everybody else in the field of quasi-periodic material. And he was standing, as mentioned before, on stages saying, there are no quasi-crystals, just quasi-scientists! And 1,000 people cheer. And I was there in the crowd, sitting in the far corner. I did not cheer. Well, anyway, so he published paper after paper trying to show that these are really twins in periodic structure. I knew from day one that he was wrong, that he will be wrong several years later. And he objected quasi-periodicity for 10 years, 1984 till 1994, and then he stopped because he died. But that's not funny when somebody dies. You have to show grim face. During that period of time, there was, I'll tell you my own feelings. There were 3 periods that I felt. First, I felt, wow, that the great scientist is against me, but very soon I was not alone, so he's against us. And it was a strange feeling like this. And then the second period, I started to like it. People said, what's going on? Shechtman and Pauling are fighting up there. I liked it, the Shechtman and Pauling fighting. In the third period, I felt sorry for him. His papers against quasi-periodicity were flatly rejected. He could not publish anymore because every journal he sent, they said, Dr. Pauling, no more. This is a fait accompli, established fact that quasi-periodic materials exist. The whole community supports it. We cannot accept your papers. And he complained about it. I met him twice. I will not go into details. Both were very friendly. And my last meeting was in his home in Palo Alto, California. I gave him a talk like this for one person. He was sitting in the couch, listening to my talk with slides. Maybe some of you remember those little square slides in a box. And in 1 hour, he was just sitting there listening. At the end, he said, Dr. Shechtman, I don't know how you do that. Because he did not understand electron microscopy. And I said to him as we parted, Dr. Pauling, if you ever agree with me, please don't keep it a secret. Yeah. Okay, he died a non-believer. Okay, enough of this. I want to mention seminal contributions, Roger Penrose and Ellen Mackay. Roger Penrose with a twofold quasi-periodic array. Ellen Mackay, the great crystallographer, both live in our time in England. Ellen Mackay took Roger Penrose's tiling and made a diffraction pattern by a laser beam. He couldn't do it himself. He sent it to a friend who had a laser. Those days, somebody had a laser. I mean, now it's some who doesn't have a laser. But those days, only few had, and that friend gave him the diffraction pattern, and it has tenfold rotation symmetry. So he wrote a paper that I did not see. And the paper said, maybe there are also materials that will exhibit such a diffraction pattern. He predicted it. I didn't know about it. Ilan Blecht, Integratia John Kahn, the people who wrote the papers with me, and Dov Levine and Paul Steinhardt provided a mathematical model to quasi-periodicity, and this is why their contribution is important. I want to tell you something about this graph because it will explain to you the atmosphere during these days. The date at the bottom, as you can see, is March 1986. This is 2 years after the first publication. And a friend of mine drew it by hand and he brought it to the lunch table at NBS. This was the summer of 1986. And he wanted to throw it away. No, I said, give it to me. And I'm happy I did that. He did the following. N is the number of pages in the bibliography on quasi-periodic materials. We hired a secretary that collected the papers, actual papers from around the world, and she filed them in large cabinets, and he went in and counted the papers, the pages in the papers, and you can see the months is at the bottom. So in February we had 1 divided by n is 0.08, and so on and so forth. And this is now July of 1986, as I arrived there. And as a good scientist, he connected all the dots in one line. And to our horror, we discovered that at the end of 1986, the number of pages in the publication of quasi-crystals will reach infinity. Scientific fact, right? Good prediction. Well, it didn't happen, but the atmosphere was that the world is really exploding with activity. So enough of this. I want to summarize by the following. While order was similar to periodicity before in crystallography, now we know that order can be periodic, it can be quasi-periodic, and we listen. If somebody comes and say, hey, I have some new idea or new findings about another kind of order, we don't throw him away or her away, we listen. So this is good. I want to answer a question that you did not ask, and then if you have time you can ask questions. The question is, why quasi-periodic materials were never discovered before 1982? Why did it have to wait for me? Is it because they are very rare, or is it because they are not stable, you touch them they disintegrate, or maybe they are difficult to make and I with my magic finger made one, or they are made of rare elements, praseodymium, gadolinium, and a touch of zinc, or, so what is it? Are they rare? Not at all. There are hundreds of them, hundreds. Here's a little partial list of compositions based on aluminum, aluminum. So there are hundreds of them. They're not rare at all. Somebody could have stumbled upon one of them. Nobody did. Are they not stable? Well, yes, many are not stable, and I produced mine by rapid solidification. If you melted my alloy, it would not re-solidify as quasi-periodic material, but as aluminum 6 manganese periodic material. But many are stable, and these are a few of the stable compositions, and these are the compositions and many more that allow us to have a large crystal. They melt congruently, you re-solidify them, they were re-solidified as quasi-periodic material, so many are stable. Somebody could have stumbled upon them, but maybe they're difficult to make. Well, not at all. You can make them by casting, by retro-solidification, by single crystal growth, by electrode deposition, CVD, PVD, any technology you prepare metallic alloys, you can make quasi-periodic materials. Very simple to do. Anybody can do that. That's not the reason they were not discovered. Maybe they're made of rare elements. Not at all. They're made of iron, aluminum, chromium, copper, titanium, and more. And millions of tons of these elements are used every year in technology. Very common material. So why QCs were never discovered before 1982? It's a good question. I'll give you my answer to it. Number one, TEM. Quasi-periodic materials should have been discovered by TEM, transmission electron microscope. Why? Because in order to prepare them, we used rapid solidification. And the crystals were very small, 1 micron in size, so TEM is the tool for discovery. So you may say, okay, big deal. You know how many electron microscopies there are in the world? Well, wait a minute. Yes, there are many. But most of them are not professionals. You have to be good with electron microscopy to be prepared and to perform the set of experiments that you need to do to analyze what you have. You have to be a professional, and I was one. Tenacity. You find something interesting, don't let go. Why am I saying this? I'll tell you why. There's one scientist in Europe, when he did his PhD, he discovered my diffraction pattern. He filed it. How do I know about it? His professor, friend of mine, calls me years later. He said, Danny, you know, I have a student who discovered the tenfold rotation symmetry diffraction pattern before you. And he told me the following story. He went through the glass plates of his ex-students, pulls one, it's my diffraction pattern. He calls his ex-student and said, you know my ex-student, how are you doing? Thank you, Professor, I'm fine. How about you? Oh, I'm fine. You know, you've seen Dan Šehtman diffraction pattern before him. Said the student, of course, Professor, of course I know. Said the professor, why didn't you tell me? Said the student, you know, Professor, if I told you, you would want me to stay for 2 more years on my PhD? He filed it. That doesn't mean that he would be able to solve the issue, but he had a chance before me to do that. He didn't. So tenacity. You find something interesting, don't let go. Believe in yourself. You can believe in yourself if you're an expert in a field. And I was very good with transmission electron microscopy. I taught many classes in transmission microscopy. The theory, the practice, I still am very good in this subject. So believe in yourself if you are an expert in a field. If you are expert in thermodynamics, believe yourself, and so on and so forth. And last but not least, resilience. You know, my promotions were delayed because my university asked prominent scientists around the world should be promote Dan Šehtman for full professorship. And usually they said yes, of course, but it's very easy to destroy somebody's promotion by saying something like, well, we don't know about the Technion University, but in our university, that was the end of my promotion. So, resilience. I want to thank you very much. This is one of my grandchildren, and he created his own microscope. Thank you so much for listening to me.
Thank you, Professor Shechtman, for this amazing lecture. And in the interest of time, we can just accept
No, I find it all over the world. You're not special. When people come to us, in my culture, a question is 7 words with a question mark. Usually, people get up and give a speech. And then, when they finish 5 minutes later, they ask a question. So please just skip the speech, ask the question.
How are explained the sharp lines in quasi-crystals, having that for crystals, sharp lines, spectral lines are explained by the translation symmetry. So you need to have a large number of inputs in the diffraction pattern in order to explain sharp lines. How it is explained for quasi-crystals? Thank you.
I was wondering, what are the current uses for quasi-crystals, and what are your thoughts on the potential future uses for quasi-crystals?
Application? Okay. That's of course a question that people ask. Okay, nice, but what can we do with it? Okay, so let me I will elaborate a little bit to give you a broader picture. When a new class of materials is discovered, people start to study their properties, and people like you, each one is an expert in something. So somebody will test the electrical properties of the new materials, and somebody will test the magnetic properties, and somebody will test the thermodynamic properties, another one will test friction and wear properties, and so on and so forth. And because there are so many of them, and each one of them have been studied, all the properties of each one of them were studied widely, then there's a large collection of properties of the different structures that were found. And some of them were interesting, and when they are interesting, they can find uses. And the first use that was used immediately after my discovery is the fact that they have low surface energy, and consequently, there are no stick material, like Teflon. Some of them are like Teflon. What do you do with Teflon? You coat your frying pan. So instead of Teflon, which is a poison, you coat them with quasi-periodic alloy, and then the omelette will not stick. Better the filet mignon not stick. And the French company started to produce them. And the better side of that, I will tell you about other applications. The better side of that is an interesting story. Was a restaurant. They tested the frying pans in a restaurant in Avignon in France. And I went to that restaurant because we had a meeting there of quasi-periodic material, and we went for lunch to that restaurant, and they told the owner at the time they discovered, oh, magnifique, magnifique. So I asked him, do you like it? He said, oh, c'est magnifique, this is wonderful. And I said, what do you mean wonderful? He said, everything I make on it comes out good. I said, okay, that's the best recommendation. This was the first use, but in general, if you find materials in which the thermal conductivity differs from electrical conductivity, although both depend on electron motion, and it has good electrical conductivity but bad thermal conductivity, for instance, this can find uses in space or in other places where you need this combination of properties, and this is why it is used. The surface properties are also used by to coat different subjects that you want to have low friction and wear. Let me give an example. Two companies, Renault, car companies, Renault, French, and Fiat, the Italian company, had a joint research center. They coated the inside of cylinders with quasi-periodic material and let the engine run. When I saw it, they told me that it was running for half a year now, continuously, half a year. And I said, well, what are the results? They said, well, we didn't open it yet. We don't know. I said, will you tell me when you open it? They said, no. So I don't know if they use it or not. But this was another example of such thing. Okay. I think that for the sake of time, we should finish here. Thank you so much for listening. It is a pleasure to be here.